Hello everybody, welcome to my talk about wafers covered by DIOPTIC, an ultra-precise wavefront measurement made fast and simple for the Photonics Plus conference this year in June. My name is Roland Goschke. I'm happy that you can join me. I would like to present a system to you. This is a benchtop system that allows you to measure ultra-precise deviations from an ideal wavefront if you pass light through a cover glass, a protective glass for some measurement units. So typically those glasses should be flat on both sides, and both sides should be parallel to each other, and light that goes through the glass should not be deviating from the ideal straight line. But it actually does for anything that you hold into a ray of light that deviates at very small angles. And sometimes even the very small angles are problematic. So if you put a protective glass or cover in front of an optical measurement system that depends on the angular accuracy of the light passing through this glass, then it is important to know if these glasses are okay and not causing any large deviations. Those deviations can, for instance, originate from form deviations. If you manufacture these glasses, they can come from thermal effects by heating up and cooling down when you use those glasses in the environment. And they can also originate from heating wires that are inside those glasses, and even from the mounting of the glass to the frame. So where are these things used? They are used in so-called LiDAR systems, which is a radar that uses light, and it measures the position of, for instance, human beings or other people in traffic situations. It measures those positions with angular accuracy of a few centimeters in a distance of about 100 meters. So when you measure things with accuracies of a few centimeters 100 meters away, the smallest deviations of light are actually really important. And so the wafers cover finds those deviations on those cover glasses. If you look at these beautiful colored images, those are molding artifacts. If it's a plastic glass that's used, they are local defects inside glasses that are polished. There's also, if you use rolled material, then you can find wedge deviations. So this is light that passes through the glass and gets deviated by a few millirads. This is a few thousands of a degree. And so this is between the blue and the yellow over here. You can see the light is deviated by about 4,000ths of a degree, which is a super small deviation. But if you want to measure very accurately, this actually is a measurement, is a deviation that counts. And you can even see surface roughness influences when materials are not very well polished. There's all kinds of other causes like bubbles or stress or artifacts from injection molding where the material has a different cooling rate inside the mold. So the machine does not only have a very high resolution angular terms, it also has a very high resolution in local terms, about 2 millimeters, and it measures very fast. In fact, if you turn on a heating wire inside such a cover glass that shields a LiDAR system from ice and snow and other environmental impacts, if you turn on the heating wire, you can actually, using a wafers cover, you can actually measure how the heating goes up in deviating the light that passes through the glass. So it takes about 10 seconds, as you can see from here, for the high heating to have the full effect. And there's two causes that cause the light from deviating. It's not the heating wires itself. It's only if the heating wires are hot. They change the refractive index of the material because of the different temperature. And they also cause a thermal stress in the material that both lead to a change in the rate of the light that passes through the glass. So for very high accurate measurements, when you have to classify any transparent material that you have in a very accurate measurement system. You can use a WAVOS cover that measures with a lateral resolution of about 1 millimeter and with an angular resolution that's about 1/1500th of a degree. And it's a ready system. Unlike you go and buy a wavefront sensor, the WAVOS is already with equipped with a 200 millimeter stage. It can run multiple samples and it can run stitching measurements. And it does this in an automated way. So if you have a larger number of samples to test, you can run them on the WAVOS cover very cost efficiently, very fast. There is different operation modes. You can run in a precision mode with a resolution of 0.2 millimeters. This is the lateral resolution. You can run single shot with very fast, under 1 second measurement time. And you can run single shot calibrated, which takes about 1 to 2 seconds. And you can run larger areas by stitching and combining high resolution and high precision at reasonable measurement times. This is all factory ready and selling already into the LiDAR industry world. There's different applications in the LiDAR world, but also outside the LiDAR, where we have different machines covering that. So the standard is the 200 by 200 millimeter WAVOS cover. There is a 450 by 250 millimeter large WAVOS cover for larger covers, and there's actually a WAVOS cap for 360-degree field of view cover glasses. Those are used on construction machines, excavators that need to identify if there are persons in their moving range, and they have to stop those machines. And then, of course, for large volumes, which is 1 million pieces per year or so, there's a fully automated version of the WAVOS system. Now, outside the LiDAR world, there's other applications that I would like to present to you today, primarily for accurate mirrors that are used in setups with MEMS mirror motion projectors, for instance. Prisms are used in projectors as well, where it is crucial if those vibrating mirrors don't change their shape for the light to be reflected. So if you have a dynamic MEMS mirror setup, you can use a WAVOS to measure if those mirrors are actually changing their shape. If you have critical optical elements, could be spheres or aspheres or cylindrical lenses, you can check with a WAVOS if what those elements do is actually what they are supposed to do. So you can, in many setups, you can replace an interferometer with the WAVOS, which is the wavefront checking system, a wavefront sensor with automated software readout and go, no-go decision, depending on the integrated errors that this element generates. You can have a focusing paraboloid mirror, which if you have a point light source and shine it onto the paraboloid, it should, if the paraboloid is in a perfect shape, it should generate a perfect parallel ray of light, and the WAVOS would actually tell you if these parallel rays are parallel or not with a very high angular resolution. So it's used for very high power focusing mirrors at the Eli beam facility, where very high power lasers are combined into one spot. And WAVOS can be used to check the paraboloid quality of those focusing mirrors. Here's the WAVOS cap that I've already talked about for machines that have a 360-degree field of view. This is not easy to prove if the cover glass does not alter the light that goes through it. So what WAVOS cap does is to rotate the 360-degree cover glass and measure the entire 0 to 360-degree entire height of the cover glass. And you can see from the data here that it is super difficult to make a cover glass that does not modify the light that passes through it. So this is a very helpful tool for people who need to ensure the highest quality for their cover glasses. Okay, thank you very much. I hope that you have a lot of interesting questions. I'm standing by to answer any of your questions. And you can contact us anytime, either by email or the website or via phone. Thank you very much.